Okay, great. So these are the types of functions that we said we could integrate: pz upon qz, px upon qx, cosine x sin x. Of course, we said that q should not vanish on the real line. Okay. So that's the hypothesis that we had. So here I should write qx not equal to 0. Okay, now I will tell you something which is related to this, but it requires a slight attention. Okay, so let's do another worked out example. So to evaluate integral minus infinity to plus infinity sin x upon x dx. Okay. So I want to evaluate this integral. Now the point is, of course, this is sin x times of the form px upon qx. But the problem is here, of course, q is vanishing, p is 1, qx is x. So that vanishes on real line. That's number first issue. But what you can observe is that the sin x upon x effectively, although when I just look at the denominator x, that seems to be vanishing, but sin x upon x as a function, that does not seem to have any problem. Right? That's a holomorphic function on C, so that should not, like, it can be made continuous and all that, so there is no problem with that. Okay, but now the point is sin x vanishes at x equal to 0, so that takes care of the 0 coming from the denominator. But ideally, the way we were doing in the last case, you saw that the sine part is the imaginary part of a certain integral, and that integral was this one, this particular minus infinity to plus infinity px upon qx e power ix dx. So that's the integral we had. We took the imaginary part of that integral and we got the integral with sine. Now I can't do that anymore. Okay, so what I am trying to say, that we can't write. So if you think of writing things blindly, we can't write sin x upon x dx is imaginary part of minus infinity to infinity e power ix by x dx. So I can't write this. Okay. The point being, of course, it's the imaginary part. If you think of in that way, it's going to, the imaginary part of e power ix is sin x. So you might think, okay, that is the case. But you see, this integral does not make sense, because here the numerator is something which is, let's say, bounded, and at x equal to 0, this does not vanish. So whereas the numerator is the denominator is vanishing, but the numerator is not vanishing, right? So actually the function e power ix upon x is having some kind of singularity at 0, right? So there is some problem. I cannot directly apply this. So what we do, so this is not done, okay? Because the numerator is not vanishing. So if I can't really make sense, not the imaginary part, but rather the integral itself. Okay. So what we do is that we try to understand what happens at x equal to 0. So we know that, or we rather note that if I perturb my function little bit, okay, then I can actually work with this. So note that e power ix, so at x equal to 0, this takes value 1. So if I consider this function e power ix minus 1 divided by x, then this function is actually having now no more any problem at x equal to 0. Okay. So this function can be made continuous at 0. Okay. So if I define the value accordingly, this is going to give me a continuous function at 0. So there will not be any trouble with that anymore. Okay. So in fact, in the same spirit, you will be able to take integral of uh, minus infinity to plus infinity e power ix minus 1 by x dx. This will make sense, and then what will happen is that the sine x, so since you see the sine x by x, which was my integrand, that is still the imaginary part of this guy as well, right? So here of course my x is real number. So this is still the imaginary part. So there is, as such, we were initially supposed to take e power ix upon x, but instead, if we just subtract a 1 and then take e power ix minus 1 by x, there is nothing much that is changing. Okay, so if that's the case, we would like to say, so we want to say that I have to integrate minus infinity to plus infinity sin x upon x dx. So I would like to say that, let's say this is imaginary part of minus infinity to plus infinity e power ix minus 1 by x dx. Okay, so I would like to say this. Okay, so in order to say this, actually I need to make sure that this integral, this improper integral, converges. So let's see if I can really make sense of this improper integral, and if I can say that this improper integral is going to converge or not. Okay, so here also, of course, what I am going to do, I am going to take the limit from minus r to plus r. And I will show that that particular in that way that integral is going to converge. And anyway, as you can see, sine x upon x, that's a what do I call, that's an even function. Okay, so fine, so let's see if I can really make sense of this integral. So consider the contour. So I will take a similar contour, except that yeah, I will take this contour, etc. So I don't want to write it again, so let me just take it. Okay. I take the same contour as before. Okay, so that's my gamma r which I had. So consider the contour this, and the integral over gamma r e power iz minus 1 divided by z. So I want to consider this integral. Okay. So this function is clearly a holomorphic function, and there is no problem. Okay. So I would like to do this. Now, first of all, let's try to understand what's going on over here. So this, in this contour that I have, so I clearly, there is like, one part which is the integral on the real axis and real line, and the other part which is in the semicircle. Okay, so I am going to separate it out, and it's clear that this function has no other singularity. Anyway, z equal to 0 was one possible point of singularity, but that's not the case. It's actually holomorphic. So what I know is that this integral is 0. So clearly, by you can use Cauchy-Residue theorem, and we get that over gamma r, which is a closed curve, e power iz minus 1 divided by z is equal to actually 0. So if that's the case, then what do I get? So that implies, so that tells me I can separate into two halves. One is on the real line, one is on the arc. So that tells me integral from minus r to plus r e power ix minus 1 by x dx. This guy is actually integral over gamma r, means I am sending it to the other side. So this becomes 1 minus e power iz. So this is what, sorry, this is not gamma r, this is semicircle. Okay, so that's what I have over here. Okay, great. So I need to integrate this. So let us see if I can say something about this integral or not. Now notice this one. We have seen what we have seen before. We have seen that actually this integral over semicircle from the last class, e power iz, yeah, this e power iz divided by z, this integral on the semicircle goes to 0 as r tends to infinity. So this is from the previous analysis, whatever we have done over here, like over here. Okay, so this in this case we have seen this. We show this is the part pz by qz, that was the case. So that we have already explained in the last class. So the same true holds. Okay, so we know that this integral is actually 0 as r tends to infinity. So e power iz by z on semicircle, that goes to 0 as r tends to infinity. This is done. So therefore I have to what I have to really integrate 1 upon z on the semicircle, but that you already know how to integrate. So this is semicircle of radius r, let's say, and your theta varies between 0 to up to pi. So this guy is 0 to up to pi. F of gamma t, gamma prime t dt. So that's r e power I t. Yeah, r e power I t, and then gamma prime t is I r e power I t dt. So this is just pi times I. Okay, so therefore I know what's the integral on the semicircle. So that tells me that integral from minus r to r e power I x minus 1 upon x dx. This one I should write limit r tends to infinity. This guy is actually I times pi. Okay, and therefore this implies minus integral infinity sine x by x dx. So this one is going to, of course, that integral, now that it converges, so that's its imaginary part is going to be given by sine x upon x. So the imaginary part over here is coming out to be, you can clearly see it's coming out. Okay. So you see, in certain questions you might have to change little bit some information, like, and use your existing knowledge. Okay, so sometime questions might be exactly, it might follow directly from the formula in certain cases, but it might also happen that the you know you might have to change little bit, and you might have to keep in mind the kind of contours that you are experiencing. Okay, so look at books, you can look at other sources to get more insights about the kind of contours one takes, and you need to, for your own understanding, you need to uh, understand, like, you need to look at various kind of contours, how things are, taken care of in those places. So those kind of things you need to understand. So particularly, like I said, often on circles you would like to give certain kind of arguments, either by, let's say, Cauchy estimate, or whichever form. You would like to say that on circles certain integrals, like as you take bigger and bigger circle of bigger and bigger radius, things are going to get cancelled. So those kind of arguments you need to get used to. And then also, like, in which kind of contour what can be controlled. So all this, if you keep in your head, that will give you uh, uh, you know that will enable you to solve various kinds of problems that one encounters while taking care of the while taking care of contour integration or this kind of things. Okay, so I hope this is clear, and this convergence is done. And so you saw that this sin x upon x, which a priori does not fit in the case that we had done, but actually uses some interesting observation from there, and that finishes the job. So this is something which therefore I will end with this integral part, and then I will move to uh, calculating infinite series. Okay, so let's see what I can do. Of course, the idea is to use Cauchy residue theorem. So we will see if we can use Cauchy residue theorem and figure out some infinite sums. Okay, so that's the next segment. So evaluating infinite sums using Cauchy residue theorem. Okay, so that's the next segment. So here, let's say I would like to compute double-sided infinite series. Let's say so, like because for one-sided you have seen already, you already know any tricks, techniques to show convergence. Sometimes even you know how to figure out the limit. So suppose we are to calculate a summation n from minus infinity to plus infinity f of n. Okay, suppose I have to do that, and I would like to use Cauchy residue theorem, and then if I want to do that, you will agree that by means of Cauchy residue theorem, I could get hold of infinite sum only by only by looking at the contribution coming from the residues. Okay, so Cauchy residue theorem has two parts. One part is the integral, the other part is the sum of the residues. So of course the integral gives you integral, that's fine. So when we had to calculate certain integrals, we had used Cauchy residue theorem on certain closed contours in such a way that the integral that we desire to find, that becomes a part of that contour. And then of course with the understanding that there will be certain parameters which we will take to infinity. So that was the approach while calculating the integral. Now I want to calculate an infinite sum. So here also what will be the approach is that I am going to calculate my series uh, in means like I will take certain contour and I will take functions in such a way that the series I desire to get, that comes out as residues at certain points. So that will be the basic idea, and we are going to. So therefore, like I said, remember Cauchy residue theorem as a statement which talks about some values over some integral, and as a result it gives you some sum of the certain numbers, let's say sum of the residues. So therefore when you try to use Cauchy residue theorem to calculate certain infinite sums, what you need to do is that you need to realize, or you need to realize your sequence which you want to sum, the elements of your sequence as some residue at some point. So if you could do that, then we will be able to use Cauchy residue theorem in a successful manner, and that will solve, means like that will be like that will work out. Okay, so let's see what we can do. So therefore, to apply Cauchy residue theorem, we would like to find a function. We would like to find a function which has simple poles, let's say, at all the integers, let's say integers, and suppose n has residue f of n at n. Okay, so that will be the basic idea, that I would like to say that n is the point where I have some singularity, and there the residue comes out to be f of n. So if you apply Cauchy residue theorem, you're just going to get some 2 pi I times some of the residues and all that, and thereby you will get this sum of fn. Of course, you will only get a finite sum because we are going to take some contour, closed contour, so it will contain inside, I mean, it will enclose at most finitely many integer points, but then you can take bigger and bigger contours in the same spirit, and that will give you that, and that will give you the infinite sum. Okay, so I hope this is what means I have been like able to make it clear what I wish to do. Now, if I ask you for a function which is having simple poles at all the integers, with residue and all that, we will adjust that later. But to start with, which function will you take? The function which is having simple poles at all the integers. So the basic idea is first to find out a function which is having simple zeros at all the integers. Okay, so for that, what we do is that we consider the sine function. So sine has zeros at all the integers, and therefore if I take the reciprocal of sine, then that gives us uh, a function which is going to have poles at uh, all the integers. Okay. Anyway, so you can work with the cosine function, or you can also work with the cotangent function. Okay. So often working with the cotangent function might be easier. So that's the reason why I will take that. Okay. So consider h of z equal to pi cosine pi z divided by sine pi z. So since sine pi z has simple zeros at integers at all the integers at all the integer points, h of z has simple poles at all the integer points. Okay, and another reason why I took this cotangent function, you will see immediately that it will be very like the residue will have a very simple expression. Okay, why? So moreover, what's the residue? Residue of h of z at n. Yeah, residue at h of z is what? So the formula is, whenever we have reciprocal, the formula is a of alpha divided by p prime of alpha, right? When we have simple pole like that. So therefore, this one is pi cos pi n, and in the denominator I also have pi cos pi n. So therefore, I get the residue to be equal to 1. So that's the reason why I did this adjustment with the pi, and I also took this cosine over there, so that the residue comes out very neatly as 1. Okay, so if that's the case, then what can I say? I can say is that suppose I have a nice function. Suppose my f is a nice function, means nice in some sense, let's say. Then what I can say is that this h times f, if I consider the function h times f, suppose like I said, h is, let's say f is nice, then that's going to give me as a residue at z equal to n, the residue is going to be come out to be f of n. So this is precisely what I'm going to get, and therefore, like the idea will be that we choose a suitable closed contour in such a way that it encloses these integer points, and thereby we will try to apply, uh, you know, this Cauchy-Residue theorem and uh, get hold of our infinite series. Okay, fine. So let's see what we would like to do. So first of all, I need to of course put so once I have, so considering a new function, let's say gz. Gz will be f of z into h of z. Uh, our idea will be to construct contours enclosing, let's say 0 plus or minus 1 plus or minus 2, so on and so forth, plus or minus n, so that we get so let's say I should write contours Cn. Let me write Cn enclosing all this, so that we get, when I integrate over Cn by sorry, fz into hz. Okay, so this one is going to be 2 pi I times sum of the residues n from minus 1 to n f of n, that's what we get, and plus something. You see here, I was telling you that f needs to be some good function, okay, but let's say to ensure convergence of an infinite series, f might have to decrease, and depending on that, decrease fast, and depending on that, f can also have some kind of singularities. Okay, so I need to also take into account of those. So this will be zk uh, whole of f, let's say, okay, inside Cn, and that's going to be residue of f fz into hz, so fz into hz at zk. Okay, so this is what's the sum going to be, and of course if the zk's are pool of f inside Cn, so your n will not be equal to zk. You have to ignore that one. Anyway, so this is the formula which we can expect, and we can apply that. Okay, so of course I have not said anything about f very precisely, so those things will be clear in the question or in the examples that we will do, but nevertheless I have to put certain condition on the growth to make sure of to make sense of the convergence. Okay, so we will put some kind of hypothesis. Okay, so to ensure convergence. Okay, so I have always told you that if you have double-sided series or double-sided integral, the idea is that you will try to break them into two hubs, and both the hubs should converge. Okay, it's not that the positive side and the negative side is going to get cancelled, and thereby it's convergent. It's not that. Okay, so if that's the case, then for example, if somebody takes this series n in z minus 1 power n, then this is like this will have a definite meaning, right? Because for example, when you take will this have a limit? No. Yeah. But anyway, so you need to ensure convergence of like whenever you deal with double-sided series, or like I was telling you, improper integral from minus infinity to plus infinity, you need to have somewhere in between where you can break, and each of the things should actually converge. Okay, so that one needs to make sure. Anyway, so now, so to ensure convergence, we assume that f of z in absolute value is less than or equal to some constant divided by mod z square. So this is as mod z tends to infinity. So I assume that we have this kind of a hypothesis for my function f, and then we are going to evaluate this infinite sum. Okay, fine. So here the idea would be, you see, previously I was trying to figure out contours in such a way that the integral which you wish to calculate, that integral comes out as part of that contour. So that was the basic idea. Here the idea will be that I will try to figure out a contour in such a way so that the integral over the contour like should become close to 0. Okay. Why? Because I don't, you see, I already, my aim is to calculate this guy. Okay, so already there is this certain residues over here which are extra, which I have to calculate. Anyway, I have applied Cauchy residue theorem. If I also have to calculate this, then there are too many unknowns which I have to play with, right? Which I have to calculate and which I need to get hold of. So therefore, here the idea would be to find a contour in such a way, which I already told you that it should enclose 0, plus or minus 1, plus or minus 2, and all of that. But we should also try to make sure that somehow we get the value of the integral directly without applying Cauchy residue theorem. Because anyway, Cauchy residue theorem we are trying to use so as to get the value of the infinite series. So that's the agenda over here. And while we were calculating improper integrals, our agenda was slightly different. There we wanted to get the integral by using Cauchy residue theorem. So the contour that we were choosing the contours in such a way that the integral that we propose to find, that integral becomes part of the contour. Okay, upon taking limit, let's say. So this is the basic difference in these two kind of application, in the application for series and in the application for integrals. Okay, so I hope I have made it clear what is the agenda. So we would like to choose Cn in such a way that integral over Cn fz into xz is equal to 0, or rather goes to 0. Let me write goes to 0 as n tends to infinity. So that's the basic idea that we would like to, means this is the basic structure that we would like to have. Okay, that's fine. And once we have this, then we will use this formula, and we will therefore get this quantity in terms of this line. So again, I have to find certain residues, but that's part of the deal when we want to apply Cauchy residue theorem. Right? That's the thing which we have to do anyway. So it's about calculating certain residues. Like if I can prove this, find a Cn contour in such a way, then the evaluating infinite sum will be evaluating certain residues. Fine. So what the contour do I take? So let me again draw the xy plane and try to explain the scenario. So what I do is that let's say I mark certain points. So let's say this is n. So this is n, and let's say this is n plus 1. Let's say this is n plus 1. Similarly, let's say this is minus n. This is minus n minus 1. Over here on this line, this is minus n, and this is minus n minus 1. So these are the points that I have. Maybe I should write somewhere slightly. Yeah. So on the x-axis and the y-axis I have written. So this point is actually 0, n, 0, n plus 1, and so on and so forth, or I times n, whatever it may be. So now the contour that I want to take is through the middle of them. Yeah, so that's the contour. It's kind of going through the middle of the thing. So for example, if I have to write down the points, so this point is n plus half plus I times n plus half. This point is n plus half, then minus I times n plus half. Okay, so and then this point is minus n times half minus I times n plus half, and this one is minus n plus half plus I times n plus half. So that's the contour. Okay, and of course the orientation is going to be anti-clockwise. Okay, so here of course you see that the function f is given, the growth condition is such that mod of f of z is a into mod z square. Okay, now what is mod z over here? On the circle you or on the contour Cn, you can see that mod z is bigger than n on the rectangle that I have taken, or rather the square that I have taken. On that, the modulus is bigger than n. Okay, so therefore the bound about f is, so note on Cn, mod of f z is less than or equal to some constant a by n square. Okay, so that's what it is. Okay, that's number one. And moreover, the length of Cn. What is length of Cn? So length of Cn is about some constant. So it's some constant times n, because that's the circumference, right? Here, I think each side is of length 2n plus 1, right? So 4 times 2n plus 1. So yeah, 4 times 2n plus 1. So anyway, so the length of the curve is some constant times n. Now, if I want to apply ML inequality on Cn, so I got a bound for f, I got a bound for the length of the contour. So what I need to bound? I now need to bound the guy which is h of z. So what is h of z? H of z is pi cot pi z. So effectively, what I need to do now is to bound this function pi cot pi z. If I can do that, then we will be done. So that's what I really need to do. Okay, all good. So let's see if I can do that. Okay, so what do I do about now? The cotangent. Fine. So note um, cotangent for pi z. I can write this as cosine by sine. So that is e power I pi z plus e power minus I pi z divided by 2 e power I pi z minus e power minus I pi z divided by 2i. So this is I times 2 gets cancelled. I can take out e power minus I pi z common. So this is e to the power 2 pi I z minus 1 and e to the power 2 pi, sorry, plus 1 2 pi I z minus 1. So that's the quantity which I have over here. Okay, all good. So now I am going to make some estimates depending on in which portion of the contour Cn I am in. Okay, so this is my contour Cn. Remember that that's my contour Cn. So on this contour there are four lines, actually four straight lines. I would like to estimate in each of them. Okay, and then we will try to see what am I going to get. Okay, so what do I have? Let's see. So first of all, if real part of z is equal to n plus half, okay, so I am saying that the x coordinate is x plus n plus half. So that means I am on this line. So their x coordinate is n plus half. So that's what I am taking. So if that's the case, then what is z? Z is equal to, let's say, x plus iy. So this implies 2 pi iz is x is n plus half. Sorry. So therefore I need to get that's the real part. So 2 pi I n, capital N. Then I have half, so that gives me plus I pi, and then I have minus 2 pi y. That's what is 2 I pi z. Great. So what is e to the power 2 pi I z therefore? This guy is nothing but 2 power e to the power 2 pi I n e to the power I pi e to the power minus 2 pi y. So that's minus e to the power I pi is of course minus 1, and therefore, yeah, e to the power I pi is minus 1. So this is e power minus 2 pi y. That's what I have. So therefore, what is cotangent? Cotangent pi z in absolute value, I has absolute value 1. So this is 1 minus e to the power minus 2 pi y divided by I plus e to the power minus 2 pi y. That's the quantity which I have. Okay, and yeah, so this is what I get, and clearly this quantity is less than 1 because whatever is the value of the numerator, I don't care, positive, negative. The denominator, of course, exponential is always positive, so the denominator is strictly bigger than the numerator. So therefore, I get that this quantity is less than 1. So this is what precisely I get. Okay, and of course, I don't have to. You will agree that I don't have to calculate for real part of z equal to n minus half. So minus n minus half. So same calculation for real part of z is equal to minus of n plus half. Same calculation works. Fine, all good. That's okay. And now, so therefore I am done with this line. I am also done with this line. So I have to now think of the horizontal lines. So I have to take this one as well as this one. The same thing will work. Okay, so next consider. So next, let um, imaginary part of z over there is n plus 1. So that's my imaginary part. Fine, all good. So what is z? Z is x plus iy. That implies e to the power 2 pi I z is equal to 2 pi I z is 2 pi I x minus 2 pi n plus half. That's what I have. And which is what? Therefore, I can say that this is 2 pi I x minus pi into 2n plus 1. N plus 1, 2n minus 1, that will be. Okay, so what is cotangent now? Cotangent pi z in absolute value. This is I goes away. This is e to the power 2 pi I x into e to the power minus pi 2n plus 1 plus 1 e to the power 2 pi I x into e to the power minus pi 2n plus 1 minus 1. Okay, that's what I have. Okay, now by triangle inequality, I know that something a plus b in absolute value is less than or equal to mod a plus mod b. So this is less than or equal to, if I take mod a plus mod b, this is going to give me 1 plus e to the power minus pi 2n plus 1. Okay, that's good. And in the numerator, I have mod of a minus b. Now you know that mod of a minus b is bigger than or equal to mod of mod a minus mod b. Okay, so this is something which we always know. So therefore, here in this case, this becomes 1 minus, because you will see that for other one, it's always less than 0. Uh, Sorry, it's always less than 1, because so I can write that this is minus pi to n plus 1. So this is negative quantity, so exponential of that is less than 1. So this is the bound that I get. Okay, 1 plus something and 1 minus something. Okay, all good. So now anyway, here one thing that I have, notice that as n tends to infinity, can anybody tell me where does this going to go to? As n tends to infinity, where does this ratio going to go to? Yeah, anybody is listening or everybody is? Hello, are you guys there? Can you tell me where does this limit go to?
One.
It goes to 1. So if it goes to 1, then that means what it says, that I, in absolute value, I have something which is having an upper bound. So that sequence is bounded above, it's going to 1. So for all practical purposes, I can say cot pi z is going to be on that imaginary axis. It's going to be bounded above by 1, or you can say bounded above by 2, let's say. So we can take in large enough to ensure mod of quad pi z is less than 2 on imaginary part of z equal to n plus half. Of course, there is no uh, difference if I take imaginary part of z is minus half. So there is absolutely no difference. This is what we have. Okay, so therefore, whatever be the case, I saw first, then on these two lines, the cotangent was less than 1, and now I have seen on these two lines the cotangent is less than 2 in absolute value. So therefore, like of course there was a pi multiplied with it, but effectively what I see is that this h function on the contour, this h guy on the contour is bounded, is a bounded function like independent of n. I can bound it, and therefore hence by ML inequality integral over Cn of fz into hz is equal goes to 0 as n tends to infinity. So as that happens, we are going to get this. Okay, and so if that's the case, if this integral goes to 0 as n tends to infinity, therefore it tells me all the all possible things that I can expect. So like that essentially gives me the formula. So hence what I get n in z, n not equal to zk, zk poles of all, like singularity of f of n is equal to minus the sum of the residues of f. So here I am not writing h. Let me write the actual function because you can treat this as the formula zk poles or whatever, singularity. Okay, so that's the formula that we have over here. That if I need to sum this, sum over f of n, sum of f of n as n varies over z, I get that this is going to be this residue minus residue fz pi or pi z comma zk, where zk's are singularities of n. So this is what you can calculate and see. Okay, so I will do some examples just in a bit. Okay, but let me just do one more case and then I will tell you about some examples. Okay, in the same spirit, I can also do another one. So what is that? Here I was evaluating this summation fn n from minus infinity to plus infinity. So you can also evaluate. So we can also evaluate summation n from minus infinity to plus infinity minus 1 power n f of n. We can also evaluate this infinite sum. Okay, so here therefore what's the requirement? The requirement initially, if you remember, I found out if you go back to the beginning, you saw I started with a function h which was having simple poles at integer points and the residue was 1. Okay, and so when we multiplied with f, that gave us residue f of n. And this time we want to sum minus 1 power n times f of n. So what would be our job? Our job would be to find function which has singularity, simple poles at let's say all integer points, and the residue should be minus 1 power n. Okay, so that's the thing which we would like to do. So in this case, what we actually do is the following. So here I told you multiplying with this cosine had the benefit that the residue came out to be 1. Okay. Now, if you do not take this cosine, okay, in this particular case, instead you just think of 1 upon sine. Okay, so if h of z is equal to, let's say, pi by sine n sine pi z, then h has simple poles at all the integers. Now what's the residue? With residue, so Here, how am I supposed to find the residue? Again, the same principle. The numerator should should be evaluated at that point. Denominator needs to be like you need to take the derivative of the denominator and evaluate at that point with residue pi divided by pi cos pi n. Okay. Now, what is cos pi n? If you can recall the value, cos pi n is actually nothing but minus 1 power n. Okay, because yeah, cos 0 is 1, cos pi is minus 1, cos 2 pi is 1 again. So the residue here is minus 1 power n. That's my 8. So, and now you need to notice one thing. We know that cotangent and cosine and cotangent, they are related, right? So once I know that cotangent is bounded, I will also know that cosec is also bounded. Okay. So here the function that I have is pi cosec pi z and cosine pi z. Sorry, yeah, pi cosec pi z cosecant. So what's the formula? I have forgotten. I think cot square plus 1 is equal to cosec square, right? So I anyway know that cotangent is bounded, so I will get that cosecant is bounded, and therefore the same analysis that I have done, everything is going to work exactly the same way, except that wherever I had cotangent, I'm just going to replace it by cosecant. Okay, so by the same analysis we get integral over Cn f of z into pi into cosec pi z goes to 0 as n tends to infinity, as cosec pi z is also bounded on Cn. Okay, so exactly the same analysis, it gives you this goes to 0. Okay, hence because yeah, exactly 1 plus cot square is cosec square, so the same like if cot is bounded above by 1, then cosec is going to be bounded above by 2. If cot is bounded above by 2, cosec is going to be bounded above by or like square root 2 or whatever, square root 5. Anyway, so it's going to be bounded. That's all that we need. And hence, once I have that, hence Cauchy residue theorem implies summation n in z minus 1 power n f of n, n not equal to zk, is actually minus zk singularity of f. This one is zk sum over zk singularity of f, residue of pi cosec pi z into f of z z. Okay, so that's the formula that we can have. Okay, so here to do this, to really apply these two theorems or these two formulas that I have said, what is necessary? The necessary thing is to be able to calculate these two residues of fz into pi cot pi z and residues of fz into pi cosec pi z. You need to find out these residues. Now suppose f is given to you, let's say 1 over z square or 1 over z cube, you can immediately find the residue for f, but you need to calculate the residue for pi cosec pi z into fz. So for that purpose, it is important that you note down the uh, you know expansion of cotangent and like Laura expansion of cotangent and cosecant at z equal to 0. Okay, so I do not quite remember now what is the expansion. So knowing that expansion helps. Okay, so I think this you please check yourself. So I think cot z is 1 by z minus z by 3 minus 1 by 45 z cube and some plus dot dot dot. Let me just check once. I think and need both. So just see. Yeah, I think this is z cube. Let me also write down a few more terms. I think minus 2 by 945 z power 5 and so on and so forth. Okay, so this is I think for cotangent, and I do not remember for cosecant what it is. Um, but you
1 by z plus 8 by 6.
yeah, exactly. So, what's the idea of doing that? You know the power series expansion for sine. Okay, so you should see sine into cosine should give you 1. So, you can equate and figure out also. So cosec z will be I think 1 over z because sine will have a 0 there at z equal to 0, and then I think plus z by 6 and I do not remember now.
7 by 360 z cube.
Anyway, so so on and so forth. Of course, all of them are odd functions, so only odd powers are going to be there. Even powers are not going to be there. But anyway, so using like keeping these informations are useful because it like at a time where you want to figure out these residues, whether you can calculate or you can differentiate, of course, depending on the function that you have. If that's easier, you can do that, and I have already told you the formulas, so you can use them and figure out the residue. Otherwise, of course, knowing the Lora expansion also helps. Okay, so if you know the Lora expansion, you will be able to do it easily, and therefore like these are the Nora expansions that we have. You can see that. Okay, so once you have this, how can I, for example, do some problems like so let's have this information in place and let us do some examples. uh, so for example, calculate summation n bigger than or equal to 1 minus 1 power n by n square. Okay, so here, of course, for alternating series, you know that minus 1 power n by n itself is convergent, but I need to have denominator having exponent more than 1. Okay, because uh, the way I have applied ml inequality, you saw that the way I had applied ml inequality over here, I really had f of z is mod of a by n square, and my cn, sorry, my c subscript n was roughly about c times n. So therefore, what I really need is that when I multiply f into the means like the m of gamma is a by n square, uh, like some constant divided by n square. Length of the gamma is some constant times n. So I really need some factor to be there which makes that m gamma into l gamma going to go to 0, like upon applying ml inequality. So here I really need, in place of 2, I means like I will be able to work with anything which is 1 plus epsilon, epsilon positive. So that is must. So just one, barely one, will not give me anything. So here this is minus 1 power n divided by n square. So how do I find this? So clearly this seems to be something which is even. So I can write that this guy is actually half of summation n over z, n not equal to 0, minus 1 power n divided by n square. Okay, so this is what I have, and therefore what do I get? I get that this term is therefore, by the formula, is actually half times, there is a minus, and residue, of course, f has only one singularity, which is at, like here my f is 1 over z square, so that has only one singularity, which is at z equal to 0. So I need to calculate residue of pi cosec pi z divided by z square at 0. So I need to calculate this. Okay, so already cosec has a singularity of uh, order 1 at z equal to 0, because sine has a simple 0 at z equal to 0. So cosecant has a simple pole at z equal to 0, and when I am dividing by z square, I am getting a pole of order 3. Okay, so if I do this, so now you can imagine, if I replace pi over here, everywhere there will be pi, and then I need to divide by z square. So if I divide by z square, this will be cubed, and this will, I will get 1z in the denominator, and I have to multiply by another pi, so it will become pi square. So effectively this residue seem to be coming to pi square by 6 with a minus half, so minus pi square by 12. So that's the sum which I am going to get working. So you see, it was quite easy once I knew the LoRa expansion of cosecant. Okay, so it depends in which form you have. You can of course try to use uh, derivative technique. Okay, so it's a pole of order 3. You can take the derivative twice, and then you can use the formula and get the residue. That is fine, all good, no issues. But if you know the LoRa expansion of cosec and all that, so using that also you can do it. So similarly, you can of course calculate in the same spirit. um, so let's do this. Calculate summation n bigger than or equal to 1 over n square. So if I have to calculate this one, I will write this guy as, so this is equal, so I have to calculate this. So I'm going to write that this term is half of summation n in z, n not equal to 0, 1 upon n square. That's the case, and therefore this is going to be minus half residue of pi cot pi z into divided by z square at 0. Again, cot pi z has, so that's caused by sine, so it has a simple pole at z equal to 0. So dividing by z square, it has a pole of order 3 at z equal to 0. And if you divide by z square over here, you will get what is the coefficient. It's going to be minus 1 over 3, and this is going to be minus half into minus pi by pi square by 3 minus, so that's going to be pi square by 6. Okay, so accordingly you will get these values. So this quantity is pi square by 6. You probably have seen this before as well. This is special value of the Riemann zeta function, or if you have heard of Basel problem, it's Basel problem was about evaluating this particular infinite series. Okay, so I'll just finish by giving some exercises for you to do. Okay, I have uploaded a tutorial sheet where probably I have given some exercises. Uh, so you can also do these ones. Summation n bigger than or equal to 1, 1 upon n power 4. Okay, so these are numeric questions. This is something which I wish that you don't miss out on these things, because these are effectively some calculation. It's not theory. It's rather calculation. So try to calculate this infinite sum using Cauchy residual theorem. Okay. So I will probably stop here, because next, as I said, I thought of telling you about infinite products, but I will not have any more time. And like, if you guys are really interested to have a class on Monday, I can take that. But otherwise, the syllabus that we had to cover, that is kind of done. Okay. So it was mainly the last segment was mainly about looking at application of what is called the Cauchy residue theorem. We have seen some theoretical applications like Roussey's theorem, argument principle, and all of that. We have also seen some practical applications like evaluating integrals, evaluating infinite sums. So the syllabus is complete, but it's completely up to you guys. You can tell me over email if you want to meet on Monday. Of course, your exam starts from probably Tuesday. I do not know what is your schedule, but if you guys want to meet on Monday, I will be happy to meet you. But those portions are, even if we discuss something on Monday, I will not put it in the syllabus. So the syllabus, the entire syllabus is like the course is ending here. You should do the problems. More number of problems you do, the better it is. And I will not put anything extra other than this part of the syllabus. Okay, so is this understood? Yes, I'll stop the recording over here. And